What if your whole life never happened? Not ended, not erased, simply never took place at all? What if you came into existence a single moment ago, already carrying the face of everyone who ever raised you, already sure of the town you grew up in, already certain of the mistakes you are still quietly ashamed of, and every one of those memories was assembled from nothing in the same instant you began to have it? There would be no seam to notice, no gap in the reel where the truth might leak through. A mind stitched together this way arrives, finished, furnished, fully convinced, holding a lifetime it never had a single afternoon to actually live. And here is the part that should keep you awake. Serious physicists have a formal name for that exact possibility. They call it the Boltzmann brain, and it is not a joke told at the back of a lecture hall. It sits inside real equations, in real published papers, written by some of the same people who calculate the long-term fate of the entire universe. It is serious enough that a few of them have had to stop and ask an uncomfortable question about their own best theories. If our math is right, why are you not one of these accidents? Why is anyone? That is where we are going tonight, and I want to be honest with you about the shape of it before we start, because the journey is stranger than the destination. This is not a story about the universe ending. Endings are almost comforting. An ending assumes there was something real that lasted long enough to finish. What follows is stranger than an ending. It is the possibility, taken seriously by working scientists, that a whole convincing life was always cheaper for the universe to fake for one lonely mind than it ever was to build in full for billions of us across billions of years. And the trail that leads there is lined with real people. A physicist buried in Vienna under an equation carved into his gravestone that he never actually wrote. A young man working alone on a December night in 1979 who scrawled 2 words across the top of his notebook because he needed to convince himself of what he had just found. A scientist who bet on the fate of the cosmos 10 years before anyone could check him, and who won. A mountaintop in Arizona where 30 million galaxies just quietly cracked a law everyone thought was fixed forever. A shopping mall that a little boy was never once lost in, remembered later in perfect, tender detail. And a demon dreamed up 400 years ago by a man alone in a room. A demon that modern physics has, almost by accident, made real. By the end, you will have walked through every one of those, and you will understand exactly how seriously the idea is meant, and exactly where the science runs out and hands the rest to you. Because underneath all of it is one question, and it is yours to answer, not mine. Every proof you own that your past really happened lives inside your head, right now, in this moment. If a mind can arrive already full of a life it never earned, what test could you possibly run from the inside to tell a real life from a beautifully convincing one? The answer waits at the very end, once you have the tools to reach it yourself. Before we begin, if you enjoy these topics as much as we do, make sure to like the video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Somewhere in the cold, thinning dark between the galaxies, far from any star, far from any planet, in a stretch of space so empty it is nearly a perfect vacuum, a thought forms, not in a body, not in a skull. There is no body, and there is no skull. There is only, for the briefest possible moment, a pattern. A specific arrangement of particles that happens to hold a full human mind, complete with the sensation of sitting somewhere warm, complete with a name it believes is its own, complete with the memory of a mother's voice and a childhood bedroom and an argument left unfinished years ago. None of it happened. The mind has no years behind it. It has no mother. It has existed for a fraction of a second, and it will exist for a fraction of a second more. And in that sliver of time, it is utterly certain that it has lived a whole life. Then the particles drift apart, the pattern dissolves, and the dark goes back to being empty, as if the thought had never been. This is not a scene from a film. It is a scenario that appears, written in plain mathematics, in the research literature of modern cosmology. And the physicists who put it there were not trying to frighten anyone. They were trying to check whether their own equations could be trusted. The idea has a name. In the papers, in the seminars, in the arguments that spill out of them, it is called the Boltzmann brain. A single, self-aware mind that assembles itself out of random chance, arriving already loaded with false memories of a past it never had. And the reason it matters is not the reason you would first guess. The worry has never really been that you, personally, are one of these things flickering in the void. The worry is far more clinical and, in a strange way, far worse. The worry is that our best current models of the universe, the same ones we use to describe how the cosmos began and how it will end, keep quietly predicting that minds like this should vastly outnumber minds like yours. That across the enormous span of everything, the accidental, memory-stuffed, momentary minds should be common, and the real ones, the ones grown slowly over billions of years, should be almost unimaginably rare. If that prediction is right, then a randomly chosen observer, chosen from all the observers the universe ever produces, should almost certainly be one of the accidents. And you are an observer. That is the shape of the problem, and it does not go away just because nobody likes where it points. Let me be precise about who takes this seriously, because the instinct is to assume this lives at the fringe, whispered by the kind of people who also believe the moon landing was staged. It does not. One of the clearest voices on it belongs to the physicist Sean Carroll, who has spent years working through what to actually do with the result. His concern, stated carefully and repeatedly, is never that you should lie awake convinced you are a brain in the void. His concern is structural. Any serious model of the universe that predicts most of its observers should be random fluctuations, has, in his words, a serious problem on its hands. Either the model is broken somewhere, or something we do not yet understand is quietly keeping it from being true. That is the whole point. The Boltzmann brain is not a claim, it is a symptom. It is the fever that tells a doctor something underneath is wrong. To feel why a physicist would treat this the way an engineer treats a crack in a load-bearing wall, you have to understand what kind of statement it actually is. It is not a measurement. Nobody has detected a Boltzmann brain, and nobody expects to. It is a prediction that falls out of otherwise trustworthy math when you run that math to its conclusion. Think of it like a bridge design. An engineer draws up the plans, runs the numbers, and the numbers say the bridge, under its own weight alone, on a still day with no traffic, will collapse. The engineer does not conclude that bridges are haunted. The engineer concludes that something in the design is wrong and refuses to build until it is found. That is exactly the posture serious cosmologists take here. A theory that predicts an overwhelming flood of accidental minds is a theory failing a basic test of self-consistency. It needs fixing, or it needs abandoning, no matter how elegant it looked before you noticed. And the strangest part, the part that makes this more than an abstract worry, is how little the universe would actually need to spend to make one of these minds. Your intuition says a conscious observer is an enormous, expensive thing. It took a galaxy, and a star, and a planet, and 4 billion years of biology to produce the one currently reading these words. Surely that is the natural cost of a mind. But nature does not care about the story that produced a pattern. It only cares about the pattern, and a pattern that holds a single mind for a single instant, complete with a lifetime of false memories, is a staggeringly smaller and cheaper thing for random chance to stumble into than an entire functioning cosmos full of real galaxies and real history. Far smaller, far more forgiving to the odds. If chance can, given enough time, assemble a whole universe by accident, then it can far more easily assemble the much simpler thing, just the mind, just the certainty, just the memories without any of the years it would take to earn them. There is a common reflex at this point, and it is worth naming, because it feels like an escape and it is not. The reflex is to say, but I remember my life in detail, it is rich and consistent and full, so I cannot be one of these flickering accidents. Look hard at that for one honest second. The false memories are not imagined as thin or sketchy. They are imagined as complete. That is the entire premise. A mind that fluctuates into being holding a fabricated past, holds it exactly as vividly as you hold yours right now. The richness of your memory is not evidence that it is real. It is precisely the thing the scenario says can be counterfeited without a single flaw you could ever detect from the inside. The vividness is not your alibi. It is the forgery working as designed. So the question sharpens into something with teeth. Not, do I feel real? You will always feel real. The question is whether the universe, run according to our own best physics, tends to produce far more minds that only feel real than minds that actually are, and if it does, why you should trust that you landed in the rare, genuine group. That is not a riddle a poet invented. It is a counting problem, and physicists know how to do counting problems, and when they do this one, the numbers keep landing somewhere nobody wants them to land. Here is the honest resolution of this first piece, delivered plainly, because this chapter owes you an answer, and not just a chill. Nobody has proven you are a Boltzmann brain. Physicists have been consistently, deliberately careful never to claim that. What the field has actually established is narrower and, in its own way, more unsettling than a yes. It is this. As of right now, nobody has a fully agreed upon way of counting observers across a vast or eternal universe that cleanly avoids predicting an excess of exactly these accidental minds, without simply being tuned after the fact to dodge that one conclusion. That is the real state of things, not proof of doom, a gap. A live, unsolved technical gap sitting inside working equations that are otherwise among the most successful humanity has ever written. The people holding those equations are not cranks. They are, in many cases, the very people who built modern cosmology. And they are still checking right now whether the universe they discovered has quietly made you one of its accidents. None of this would carry any weight if it rested on the word of one man, and it does not. But it did begin with one man, an Austrian physicist whose name is now attached to the whole idea, though the idea was only a small, almost offhand part of what he actually did. He built the mathematics of disorder itself, the machinery that lets you count how many ways a thing can fall apart. And it is that machinery, more than a century later, that lets anyone calculate how often a stray mind should assemble out of nothing. He never got to see where his work would travel. He died before the final proof of his life's central claim arrived, and by then he had already spent decades being told his most important idea was not even real. His name was Ludwig Boltzmann. And to understand why an equation carved onto his gravestone in Vienna is not quite the triumph it looks like, you have to go stand at that grave. In the central cemetery of Vienna, among the graves of composers and statesmen, there is a white marble bust of a man with a heavy beard and tired eyes, and above his carved head, cut cleanly into the stone, sits a short mathematical equation. It is one of the most important formulas ever written. It relates the disorder of any physical system to the number of different ways the pieces of that system can be arranged. And it is the reason we can say, with precision, why a broken glass never reassembles and why heat never flows on its own from something cold into something hot. The man beneath it is Ludwig Boltzmann, and from 10 steps away the grave looks like exactly what it should be, a monument to a man who won. Walk closer, and the story turns quietly, unbearably strange. Because the equation carved above his head, the one the whole world now associates with his name, contains a specific number that Boltzmann himself never used and never wrote. Someone else added it, years after he was dead, and it has been standing over him ever since, in a stranger's handwriting forged in his honor. The number is called Boltzmann's constant. It is a tiny, fixed quantity that links the temperature of a thing to the energy of its jostling particles, and it appears in physics equations across the entire field. Everyone calls it Boltzmann's constant. Boltzmann appears never to have used it. The constant was introduced into the equation years later by Max Planck, who was solving a completely separate problem in the year 1900, and Planck admitted this himself, openly, in his own Nobel lecture in 1920. As far as anyone can tell, the man whose grave carries this formula as a kind of eternal signature never once put that constant into it. So the equation on the stone is not really his signature at all. It is someone else's handwriting. arranged into a tribute, placed on a grave he can no longer argue with. There is something almost cruel in the neatness of it. The man who spent his life explaining exactly how order decays into disorder did not even get the final tidy word on the summary of his own life's work. To understand why that detail lands so hard, you have to understand what Boltzmann was actually fighting for, and how alone he often was in the fight. He believed something that sounds obvious now and sounded close to heresy then. He believed that atoms were real, not a convenient bookkeeping trick, not a useful fiction for balancing chemical equations, but genuine physical objects, tiny discrete lumps of matter that everything is built from. Today, that is simply true, taught to children. In the last decades of the 1800s, it was a live and bitter controversy, and some of the most respected scientists in Europe were on the other side. There was a whole school of thought called energetics, led by the chemist Wilhelm Ostwald and given its philosophical spine by the physicist Ernst Mach, that held atoms to be an unnecessary hypothesis. Everything you could actually observe, they argued, could be described in terms of energy alone, without ever assuming matter was secretly made of little particles nobody had ever seen. Boltzmann thought this was not just mistaken but backward, a refusal to believe in the very thing his mathematics described. The two sides collided in public, and the most famous collision came at a scientific meeting in the German town of Lübeck in 1895. Boltzmann stood on one side, defending the reality of atoms. Ostwald and his allies stood on the other. A young physicist in the room named Arnold Sommerfeld, who would go on to become a giant in his own right, described the clash in a single line that has outlived almost everything else said that day. The fight between Boltzmann and Ostwald, he wrote, resembled the struggle between a bull and a supple fencer. Boltzmann was the bull. Raw force, deep conviction, the weight of the mathematics behind him, and by most accounts, he carried the room that afternoon. He was right, and on that day it showed. But winning the room did not end anything. The attacks kept coming. In journals, in lecture halls, in the slow, quiet machinery of academic reputation. For years, victory on paper never once translated into peace. And Boltzmann, by every account, was a man for whom peace was already hard to hold. He was not a cold or bitter figure. The people who knew him described someone warm, funny, generous, a beloved teacher whose students adored him. But those same people watched something else move through him on its own schedule, indifferent to how well or how badly his life was going at any given moment. Stretches of restless, almost feverish productivity would give way, without warning, to collapses into a depression severe enough to frighten his family. Historians looking back through his letters and his behavior now suspect what today would be recognized as bipolar disorder, decades before there was any clinical name for it. And long before there was anything resembling treatment, the instability was not caused by the atomism war. It came and went regardless, but the war gave it something to grind against, and every fresh round of criticism landed on a man who was already, at times, barely enduring it. There is a version of this story that most people already believe, the one repeated in classrooms and popular books, and it goes like this. Boltzmann was mocked, ignored, and hounded to death by a scientific community that refused to take him seriously. A lonely genius destroyed by small-minded rivals. It makes a clean and satisfying tragedy. It is also not true, at least not the way it is usually told. By any objective measure, Boltzmann was one of the most recognized physicists of his era. In 1888, he was offered a prestigious chair in Berlin and turned it down. Universities in Leipzig, Munich, and Vienna competed openly for him, dangling salaries most professors could only dream of. He collected medals, honorary degrees, invitations from across the continent. The energetics fight was real, and it was ugly. But the historians who have gone back carefully through the record find no evidence that he was ever genuinely ignored. The clean morality tale needs a villain, and the villain it invented, a world that refused to listen, simply was not there. What actually wore him down ran deeper than citations or conference debates. and there is a haunting glimpse of it in his own words. In notes reconstructed from one of his own lectures, given in October of 1904, Boltzmann can be found wrestling with something close to a warning about himself. Philosophy, he said, got on his nerves, because analyzing the ultimate ground of everything eventually made everything fall into nothingness. He decided to keep teaching anyway, to look the hydra of doubt straight in the eye. And then, as a joke, he added that doing so could be quite ominous if one valued one's life. He was laughing at the edge of something. 6 years earlier, in 1900, while working in Leipzig, he had made his first attempt on his own life. He survived it, returned to his lectures, and the ordinary rhythm of his career resumed, almost as if nothing had happened. The standards of the time offered him almost nothing in the way of real help for what he was carrying. In early September of 1906, Boltzmann traveled with his wife and daughter to Duino, a small coastal town near Trieste, for what was meant to be an ordinary family holiday by the sea. On the 5th of September, while his wife and daughter were out swimming in the water nearby, Ludwig Boltzmann died by suicide. He was 62 years old. There is no tidy explanation for why that particular day, in that particular place, became the end, and the honest record does not supply one villain to blame it on. What the evidence supports is a private, years-long struggle that had little to do with atoms or entropy or academic rivalries at all. Physics did not kill him. It simply never got the chance to hand him the one piece of vindication that might, conceivably, have helped him hold on a little longer, because that vindication was already on its way. The definitive proof that the atoms he had defended his whole life were real, physical things was assembled almost immediately after he was no longer alive to receive it, by a young patent clerk named Albert Einstein and a French experimenter with a microscope. He missed it by 2 or 3 years. That is where this grave leaves us, standing in a Vienna cemetery in front of a formula in a dead man's name that a living man completed. But the deeper thread runs on past the marble. The mathematics Boltzmann built to describe something as small and ordinary as a jar of warm gas did not stay small and ordinary. It turned out to describe the disorder of the entire universe, and eventually, in hands he could never have imagined, it became the exact tool that lets physicists calculate how a lonely mind might assemble itself out of empty space. To follow it there, we have to leave the man behind and go back to the one iron rule his equation was built to measure, the single most tested, most unbroken law in all of science, the one your own body is quietly obeying at this very moment. Pour a little milk into a cup of black coffee and watch what happens. For a second or two there is structure, a pale cloud unfurling, curling ribbons of white spiraling through the dark. Then it settles. Within a few seconds the whole cup is an even, uniform brown, and it stays that way. Now, here is the thing worth noticing. You could sit and stare at that cup for the rest of your life, and your children could stare at it after you, and none of you would ever once see the milk and the coffee separate themselves back out into cream on top and black beneath. The mixing happens easily, instantly, on its own. The unmixing never happens at all. That simple, stupid fact about a coffee cup is one of the deepest truths in physics, and it points in a single direction that the entire universe is willing to move, and only one, toward mixing. Toward evening out. Toward less structure, never more. This is the second law of thermodynamics, and it does not negotiate. The rule was not handed down from the stars. It was dug out of the grime of the Industrial Revolution by a man trying to answer a narrow, dirty, practical question. His name was Sadi Carnot, a French military engineer, and in 1824 he sat down to figure out why steam engines always waste fuel, no matter how well they are built. Not why badly built ones waste fuel, that is obvious. Why even a perfect one must. His answer, buried in a slim book almost nobody read at the time, became the seed of everything that followed. Heat, he realized, cannot be turned entirely into useful work. Some of it always leaks away, flowing from hot to cold, and no design, however brilliant, ever closes that gap to zero. There is a tax on every engine, and the tax is written into the fabric of nature, not into the quality of the engineering. Decades later, two other physicists took Carnot's stubborn little fact about pistons and blew it up into a statement about the whole cosmos. Rudolf Clausius, the same German physicist who would later coin the word entropy, and William Thomson, the Scottish physicist better known to history as Lord Kelvin, saw that this was not really about engines at all. It was about the direction of everything. Heat flows one way, structure decays into disorder. And crucially, this is not a tendency, not a preference, not a rule of thumb with occasional exceptions. It is as close to absolute as physics gets. In 1928, the astronomer Arthur Eddington gave it the grandest endorsement in the history of science. He called the second law the supreme position among the laws of nature, and warned that if your pet theory is found to contradict it, then there is nothing for it but to collapse in deepest humiliation. That is not the language of scientific enthusiasm. That is a field telling you exactly how seriously it takes one single rule. The word Clausius reached for, entropy, deserves a careful look because almost everyone misunderstands it. It sounds abstract, like a mood or a metaphor, a vague poetic gesture at decay. It is nothing of the kind. Entropy is a literal count. It measures the number of different ways the pieces of a system can be rearranged while still looking, from the outside, like the same overall state. Picture a child's bedroom. There is essentially one arrangement of that room that counts as perfectly tidy, every toy in its exact place. But there are countless millions of arrangements that count as messy, toys scattered in every possible position across the floor. That is the whole secret. Messy is not a curse, and tidy is not a virtue. Messy simply describes vastly more possible arrangements than tidy does. And so, if things are shuffled at random, messy wins every single time, by sheer overwhelming weight of numbers. Nobody has to make the room messy. Chance does it, because there are so many more ways to be messy than to be neat. This is exactly what Boltzmann proved, with mathematical precision, in 1877, turning a vague philosophical worry into hard, countable numbers. His equation, the one on the Vienna gravestone, says that the entropy of a system is set by the number of ways its pieces can be arranged. High entropy just means an enormous number of possible arrangements. Low entropy means very few, and the second law, in this deeper reading, stops being a mysterious cosmic decree and becomes almost boringly obvious. Systems drift from arrangements. There are few of toward. Arrangements, there are many of. For the same reason, a shuffled deck of cards comes out, jumbled rather than sorted. A perfectly ordered deck is not forbidden. It is simply one arrangement out of an almost unimaginable number, and the jumble wins by pure counting. And this is where the coffee cup stops being a kitchen curiosity and starts being a mirror, because the same law is running through you right now at this very second. Heat is escaping through your skin into the cooler air of the room. Your cells are failing and replacing themselves imperfectly. The bonds holding your molecules together are loosening, atom by atom, in ways far too small and too slow to feel. You feel solid, permanent, built to last. You are not. At the level of atoms, you are already coming apart, and you have been coming apart, quietly, since the day you were born. That is not a flaw in you. That is not bad luck. That is you obeying the most rigorously confirmed law physics has ever produced, a law that has never, anywhere, in any experiment, made a single exception. There is a way to hear all of that as bleak, and I want to reframe it, because the physics actually says something stranger and less mournful. The thing happening to your hand, to your cells, to every star burning overhead, is not decline in the sense of a machine wearing out and failing. It is participation. It is the same process that mixed the milk into the coffee, the same process that lets a wound heal into a scar instead of unhealing back into unbroken skin, the same process that gives time its very direction. Without the relentless one-way march of entropy, There would be no difference between the past and the future at all. The reason you remember yesterday and not tomorrow, the reason cause comes before effect, the reason anything happens in an order is this law. You are not the victim of the second law. You are one of the ways it expresses itself. But a law this total invites a dangerous question, and once you ask it, you cannot unask it. If everything, everywhere, is always sliding from order toward disorder, from structure toward sameness, from hot toward cold, then run that slide forward, not for a human lifetime, not for the age of a civilization. Run it forward across the entire future of the universe and ask where it ends. If the milk always mixes and never unmixes, if the engine always leaks and never gathers its lost heat back, if every difference in temperature is always evening itself out, then there is a destination waiting at the far end of time, a final state the whole cosmos is quietly walking toward. It has a name, and physicists have expected it for over a century and a half. And what makes it truly unsettling is not the ending itself. It is that we have now, in our own lifetimes, actually begun to watch it start. Take the one-way rule from the last chapter, hot to cold, order to disorder, and stop applying it to a coffee cup or a human hand. Apply it to everything. Every star, every galaxy, every black hole, every last particle in existence, all of it obeying the same relentless slide towards sameness. Run that forward far enough and you arrive at a specific, nameable place. And it is the loneliest place the mathematics of physics can describe. Every star that will ever burn will eventually burn out, its fuel spent, its light gone. The gas that might have made new stars gets used up or blown too thin to gather again. And even the black holes, the last massive structures left standing, do not last. Given enough time, they evaporate too, leaking themselves away particle by particle, even the largest of them, over a span so long that physicists write it as a 1 followed by 100 zeros in years. At the end of all that, every scrap of usable energy has spread itself so perfectly evenly across space that nothing remains capable of doing anything at all. No motion worth the name. No difference in temperature anywhere to drive a single further event. Just a cold, featureless, silent sameness, stretching on with nothing left to interrupt it, forever. This ending has a name, and the name is old. Physicists call it the heat death of the universe. Rudolf Clausius, the same man who coined the word entropy in 1865, gave this final state its own name that very same year. In German, the Wärmetod, the heat death. It has been sitting in physics as the expected terminus of everything for over 150 years. For most of that time, it was purely theoretical, a conclusion you reached by following the equations, not something anyone could point a telescope at. That is the part that has changed. In our own generation, we have begun to actually watch the process that drives us toward that ending pickup speed. We can see the engine of the long dark turning over. The moment we saw it came in 1998, and it took two rival teams of astronomers by complete surprise. Both teams were tracking a particular kind of exploding star called a Type 1a supernova. This kind of explosion is extraordinarily useful because it is bright and remarkably consistent, always detonating at close to the same true brightness, which makes it a reliable yardstick for measuring distances across billions of light years. If you know how bright the explosion truly is, and you measure how faint it looks from here, you can work out exactly how far away it happened. One team was led by the physicist Saul Perlmutter, the other was led by Brian Schmidt and Adam Rees. Both were trying to measure how fast the expansion of the universe was slowing down, because everyone assumed it must be slowing, dragged on the brakes by the collective gravity of all the matter inside it. That was the safe, boring expectation. Gravity pulls things together. The expansion should be losing steam. The supernovae refused to cooperate. They kept turning up fainter than they should have been, and therefore farther away than a universe gently slowing down could possibly explain. Both teams, working independently, checking and rechecking, arrived at the same conclusion that neither of them had gone looking for and neither of them wanted. The expansion of the universe is not slowing down. It is speeding up. Something is pushing space apart and pushing harder as time goes on, overpowering all the gravity of all the matter there is. The finding was so unexpected and so thoroughly confirmed that it reshaped cosmology from the ground up, and all three astronomers, Perlmutter, Schmidt, and Rees, shared the Nobel Prize in Physics in 2011 for it. Whatever this pushing force is, physicists gave it a placeholder name that quietly admits how little we understand it. They call it dark energy. And here is why that discovery belongs in a story about the end of everything. An accelerating expansion is a one-way ticket to the heat death, and a faster one than anyone had assumed. If space is not just expanding but expanding ever more quickly, then galaxies are being carried away from one another faster and faster. Eventually, the distant ones will be swept beyond reach entirely, their light stretched and dimmed until it can never arrive here again. The universe empties itself out. Everything drifts apart, cools down, winds down, and settles into that cold, uniform silence. And dark energy is the thing driving it there, steadily, measurably, right now. That number counting down toward a universe with no observer left standing to notice it arrive is not a philosopher's fancy. It is written into the same equations that describe your own future. And, in 1998, we measured the term that sets its pace. It is worth appreciating just how staggering that timescale is. A 1 followed by 100 zeros in years. Because in a moment, it is going to look almost modest by comparison. That number, enormous as it is, describes roughly how long it takes for the last black holes to finish evaporating and the universe to settle fully into its dead, even state. It is the length of the long dark's opening act, and a number that vast raises a strange and important question. Once everything has settled, once the last structure is gone, and the cosmos is nothing but cold, thin, evenly spread, nothing, is that truly the end of all activity? Is a perfectly empty, endlessly expanding universe finally, permanently still? You would think so. You would expect a perfect vacuum to be the very definition of nothing happening. But that expectation, it turns out, is wrong. And the reason it is wrong is the hinge on which this entire story swings. Before we get there, though, there is a loose thread in the second law that we skipped, and it matters enormously because it is the thread that lets the impossible sneak back in. Everything so far has said, the universe marches in one direction and never reverses. Milk mixes and never unmixes. Order decays and never reassembles. That is the whole engine of the heat death. But is that reversal actually forbidden? In the strict sense that the speed of light is forbidden to be exceeded, an absolute wall nothing can cross? Or is it something softer than that, something that only behaves like a law, because the odds against breaking it are so astronomically steep? This is not a small distinction. If the second law is a true wall, the heat death is simply the end, full stop. But if it is only a bet, a wildly lopsided bet dressed up to look like a law, then a bet, unlike a law, can still lose. And the man who first understood that a bet can lose was Boltzmann himself, pushed to the realization by a friend who had just tried to destroy his life's work. In 1876, Ludwig Boltzmann received an objection that should, by rights, have ended his entire theory before it properly began. It came not from a rival, not from one of the atom deniers hunting his reputation, but from a friend. His name was Joseph Loschmidt, an Austrian physicist and a close colleague, and the point he raised was so simple and so sharp that for a while it genuinely looked as though it might bring the whole edifice down. Boltzmann had built a beautiful argument that disorder must always increase, that the universe must slide one way, from order toward chaos, and never back. Loschmidt looked at the deepest layer of that argument and found a contradiction sitting right at its foundation. The contradiction was this: the fundamental equations that govern the motion of individual particles do not care about the direction of time. Take that slowly, because it is the crack that everything else in this story eventually pours through. The basic laws describing how atoms bounce and collide are what physicists call time-symmetric. Write down the equations for a swarm of particles moving and colliding. Then imagine reversing every single one of their velocities, sending each one back exactly the way it came. And the equations describe that reversed motion just as perfectly. They do not break. They do not complain. A film of colliding atoms, run backward, obeys the same laws as the film run forward. So here is Loschmidt's devastating question. If the underlying rules work equally well in both directions, then how can they possibly produce a universe that only ever runs one way? Take a gas that has just settled into a uniform, disordered, evened out state, and mathematically reverse every particle's velocity. The very same trusted equations now predict something outrageous. The gas should unmix itself, sliding right back toward the ordered state it started from, disorder flowing uphill into order. Reversible laws, Loschmidt argued, cannot possibly give birth to an irreversible universe. It seemed airtight. For a while, it looked as if Boltzmann's framework might not survive the year, undone by his own friend. Boltzmann answered the following year, in 1877, and his answer still holds up today, unbroken, more than a century later. It is one of the most important shifts in perspective in the history of science, and it did not defeat Loschmidt so much as reveal that Loschmidt was right about the equations and wrong about what they meant. Reversing a gas back into order, Boltzmann conceded, is not forbidden. Loschmidt had proven that much, and he was correct. But being not forbidden is a very different thing from being likely. Yes, the particles could all, by chance, line up their motions in exactly the pattern that would send them spiraling back into order. Nothing in the laws prevents it. It is simply one specific arrangement, one precise needle, buried inside an incomprehensibly enormous haystack of possible arrangements, almost all of which lead to more disorder, not less. The order-restoring arrangement exists. It is just so vanishingly rare against the sea of disordering arrangements that you could watch and wait across an entire human lifetime and your children's lifetimes and never once catch even a flicker of it. So Loschmidt, in trying to disprove Boltzmann, ended up proving something stranger than either man had expected. He proved that order climbing back out of chaos was never actually forbidden, it was only rare. And that single word, rare, is doing an extraordinary amount of quiet work, because until Boltzmann did the math, the only word anyone had for such a thing was impossible. The unmixing of the coffee, the gathering of scattered heat, the spontaneous return of order, all of it had been filed under things that simply do not happen. Boltzmann moved it, quietly, from the category of impossible into the category of almost unimaginably improbable. And the gap between those two words, impossible and improbable, is precisely where the rest of this story lives. It is a narrow gap. It is also, it turns out, wide enough to fit an entire universe of consequences inside. Make it concrete. Look at the air in the room around you right now. It is spread out more or less evenly, molecules bouncing everywhere at random, filling the whole space, exactly as air always does. Now here is a fact that should genuinely unsettle you. Nothing in the laws of physics forbids every one of those air molecules from happening, by pure chance, to drift into one corner of the room at the same moment, leaving you gasping in a sudden pocket of vacuum where you sit. It is allowed. The equations permit it completely. It is simply so wildly, catastrophically improbable that you could watch that room for the rest of your life, and everyone else's life, and the odds are overwhelming that you would never see it happen even once. But, and this is the whole point, wildly improbable is not the same word as never. Improbable things are still, by definition, things that happen. They just happen rarely. Wait long enough, and the room does it anyway. Exactly once. Exactly on some unthinkably distant schedule. And now stretch that same bet. Take it from a single room full of air and apply it to something the size of the entire cosmos. Then, crucially, do not run the clock for a human lifetime, or a civilization, or even the age of the universe so far. Run it for the almost inconceivable spans we met in the last chapter, the long dark stretching a 1 followed by 100 zeros of years and far, far beyond. On timescales like that, the rules of intuition break. The absurdly unlikely stops behaving like something that merely could happen and starts behaving like something that will. Every arrangement of particles that the laws of physics permit, however improbable, eventually gets its turn, given enough time. Not because the universe wants it, not because anything is guiding it, but because the word eventually, applied to an eternity, is the most patient and merciless word there is. Improbable, multiplied by forever, tips over into inevitable. There is a way to feel the vertigo of this that is worth pausing on, because it changes the character of the heat death entirely. The heat death is not, it turns out, a final resting silence where nothing ever happens again. It is a silence that is only mostly still, a stillness punctuated, on unfathomable timescales, by spontaneous flickers of order rising briefly out of the sameness and then dissolving back into it. A cosmos that has run down into featureless nothing is not truly done. It is a stage on which the improbable, given endless time, is quietly, ceaselessly rehearsing every possibility it is allowed. Given enough eternity, a patch of that dead universe could, by chance, gather itself into a swirl of order. A star's worth, a planet's worth, or, and here the temperature of the whole story drops, something far smaller and far cheaper than any of those. Because this is the loophole that leads straight to the mind in the void. If disorder is only a bet, not a law, and if a bet run across eternity must eventually lose, then somewhere in that endless dark, order will assemble itself out of pure chance. And the cheapest, most statistically forgiving thing chance can assemble that still counts as an observer is not a whole universe, and not even a whole star. It is a single mind, a momentary pattern holding a lifetime of memories it never lived. The loophole Loschmidt accidentally opened, trying to save physics from irreversibility, is the same loophole through which a Boltzmann brain steps into existence. But for that step to actually happen, one more condition has to hold. The dead, empty vacuum of the far future cannot be truly, perfectly still. It has to keep twitching forever, even after everything else has gone quiet. And whether empty space does exactly that was answered, unexpectedly, by a young physicist and the most famous mind of his generation, working at the edge of a black hole. Here is something that sounds like it cannot possibly be true. Empty space has a temperature, not the space between planets, which is full of stray gas and light and the faint warmth left over from the birth of the cosmos. Real empty space. The perfect, scoured, endless vacuum of the far future, after every star has died and every particle has spread itself thin, a place with nothing in it at all. You would expect that place to be perfectly, permanently cold. Zero temperature, zero activity, nothing left to disturb. The very definition of nothing happening. That expectation is wrong, and the man who first showed it was wrong is one you already know, working at the strangest boundary in all of physics, the edge of a black hole. His name was Stephen Hawking, and the discovery he made there quietly guarantees that the universe can never fully go still. The story begins with black holes, which had long been assumed to be the ultimate one-way doors. Anything that crosses the boundary of a black hole, the horizon, is gone forever, and nothing, not even light, comes back out. A black hole, everyone thought, could only ever grow. In the 1970s, Hawking discovered otherwise, and the discovery stunned even him. He showed that the boundary of a black hole is not perfectly black at all. Because of the strange rules that govern the quantum vacuum right at that edge, a black hole very faintly glows. It radiates a whisper of heat, and over almost incomprehensible stretches of time, that whisper drains it away, until the black hole evaporates entirely. This is the same evaporation we met in the long dark, the process that erases even the largest black holes over a 1 followed by 100 zeros of years. But the mechanism behind it turned out to be far more general than black holes, and that generality is what matters here. Working alongside the physicist Gary Gibbons, Hawking showed in the same era that the effect is not really about black holes specifically, it is about horizons. A horizon, in physics, is a boundary beyond which you cannot see, a line past which information cannot reach you. A black hole has one, at its edge. But an expanding universe has one too. In a cosmos where space is stretching apart, and especially one accelerating under dark energy, there is a limit to how far you can ever see. A cosmic horizon beyond which galaxies recede faster than their light can ever cross the growing gap. And Gibbons and Hawking showed that any horizon, black hole or cosmic, quietly radiates simply by existing. The empty space inside an expanding universe carries a faint, non-zero temperature of its own, a temperature set directly by how fast that expansion is happening. The vacuum is never truly at zero. It always, everywhere, faintly glows. The number is almost absurdly small. The temperature of the empty space in our accelerating universe is a fraction of a degree above absolute zero, so tiny it has more than 20 zeros after the decimal point before the first meaningful digit. For any practical purpose, it is indistinguishable from nothing. You could never feel it. No ordinary thermometer could ever register it. But it is not zero, and the difference between a very small number and zero in this story is the difference between an ending and no ending at all. A temperature above absolute zero, however faint, means the vacuum is never fully quiet. It is always, gently, restlessly jittering. There is always a little energy trembling through it, the way the surface of a pot of water, sitting on a warm stove well below boiling, still shivers and trembles long before it ever earns the name boiling. That faint, eternal jitter is not a poetic image. It is the actual physical mechanism, and it is the thing that keeps the door to a Boltzmann brain propped permanently open, because a jittering vacuum is a vacuum in which things can still, occasionally, happen. If empty space carried a true and perfect zero, if it were genuinely, absolutely still, then the loophole from the last chapter would slam shut. A perfectly frozen universe cannot produce spontaneous fluctuations, because there is no energy left to fluctuate. Nothing trembles, so nothing ever, by chance, arranges itself into anything. The heat death would be a real and final silence, but Gibbons and Hawking took that clean silence away. They showed that as long as the universe keeps expanding, its empty space keeps quietly trembling, forever, with a faint warmth it can never shed. And a vacuum that never stops trembling is a vacuum in which the improbable, given endless time, keeps getting rehearsed. The trembling is the engine. It is what allows something as complex as a passing thought to assemble itself out of nothing if you give it enough eternity to try. It is worth appreciating just how strange the resulting picture is. The far future of the universe is not a still photograph of death. It is a vast, dark, almost perfectly empty stage, faintly warm, faintly humming, on which random chance plays out endlessly. Almost always, nothing of interest happens. The jitter produces a stray particle here, a flicker of nothing there, and it all dissolves back into the dark. But almost always is not always. Wait long enough. On the timescales this trembling vacuum has available to it, and the flickers grow larger. Given enough of that patient, ceaseless trembling, a fluctuation could, once in an unthinkable while, assemble a coherent pattern. The room from a few chapters ago, where all the air drifts into one corner, was never really sealed off from any of this. It was just a small, fast rehearsal of the exact same restless universe surrounding it, running the identical bet on a much shorter clock. Now put the three pieces together, because they interlock into something specific and, for the physicists, alarming. First, a universe trending inexorably toward heat death, an empty, accelerating cosmos that will eventually contain nothing but faintly warm vacuum. Second, a vacuum that never fully goes quiet, that keeps trembling forever with the tiny temperature Gibbons and Hawking proved it must have. Third, stretches of time long enough to make even the most absurdly improbable event not just possible but eventually certain. Stack those three facts, and you do not get a ghost story. You get a specific mathematical description that increasingly looks like it could apply to the actual physical future of the actual universe you are living in. A future in which, given enough time, The trembling nothing will spontaneously assemble minds, and nothing about that conclusion required any exotic new physics. It fell straight out of thermodynamics and black hole radiation, and the observed acceleration of the cosmos, three of the most solid results we have. That is why the physicists could not simply wave this away as a curiosity, the way you might dismiss a fun fact at a dinner party. The moment those three well-established pieces snapped together, the Boltzmann brain stopped being a philosophical daydream and became a prediction of working equations. And a prediction has to be reckoned with, especially when it is a prediction you desperately do not want to be true. So a group of physicists sat down and did the one thing that turns a vague unease into a genuine crisis. They calculated. They asked, as precisely as the math would allow, exactly how often the trembling vacuum of an empty universe should assemble a stray mind out of noise. The number they got back was so enormous and so specific that it forced the whole question out of the shadows and onto the page in a paper with a title that did not even try to soften the blow. And that number is where this stops being uncomfortable and starts being a problem nobody in the field has been able to put down. In 2002, three physicists sat down to do a piece of arithmetic that none of them particularly wanted to finish. Their names were Lisa Dyson, Matthew Kleben, and Leonard Susskind, the last of them one of the most influential theoretical physicists alive, a founder of string theory, and a man not easily rattled. They were not writing science fiction. They were doing careful mathematics on what our universe's long-term fate actually implies about the kinds of minds that should exist inside it. And when they published, they gave the paper a title that made no attempt to hide where the math had led. They called it Disturbing Implications of a Cosmological Constant. That word, disturbing, sitting at the front of a serious physics paper, tells you almost everything about the mood in which it was written. These were not people delighting in a spooky idea. These were people reporting, with visible reluctance, that their equations kept landing somewhere nobody wanted them to land. The calculation they were running is, in outline, exactly the one the last three chapters have been building toward. Take an empty, accelerating universe, the kind ours appears to be turning into. Give it the faint, eternal vacuum temperature that Gibbons and Hawking proved it must have. Then ask how long you would have to wait, on average, for the trembling of that empty space to spontaneously assemble a single, isolated, self-aware mind out of pure random noise. It is a well-posed question. The physics needed to answer it is known, and the answer is a number so large it strains the meaning of the word number. The timescale they arrived at for a mind to fluctuate into being is written as 10 raised to the power of 10 raised to the power of 50 years. That is not 10 with 50 zeros after it. That is 10 raised to a power that itself has 50 zeros in it, a tower of exponents so tall that the human mind has no handhold on it anywhere. To even begin to place that against something familiar, hold it next to the age of the universe. The cosmos, as measured precisely by the Planck satellite, is about 13.8 billion years old. Write that out, and it is a 13 followed by a modest string of digits. Now set it beside the fluctuation timescale, the tower of exponents, 50 zeros tall, and something breaks. The age of everything that has ever happened, every war, every civilization, every sunrise since the first light in the sky, does not even register as a rounding error against that weight. It is not merely small by comparison, it is so unimaginably smaller that the two numbers do not really belong on the same page. And that, strangely, is the whole problem. Because the universe, if it keeps expanding forever, has that unthinkable stretch of time available to it. It has all of it, and more. Eventually is a longer word than any human timescale can contain. So run the two facts together and watch what they imply. Real observers, minds like yours, grown the slow way through billions of years of stars and planets and biology, are produced only during a relatively brief early window in the life of the cosmos, the window we happen to be living in now, while there are still stars and still structure. That window is enormous by human standards but finite. After it closes, the universe spends the rest of eternity as empty, trembling vacuum. And across that eternity, the vacuum keeps assembling accidental minds, one after another, forever on that tower of exponents schedule. Finite, the ordinary way. Infinite, the accidental way. Line them up, and the accidental minds do not just win. They bury the real ones by a margin with no name. If you picked an observer at random from every observer the universe ever makes, the odds that you pulled out a real one, rather than a flickering fluctuation, round to nothing. This is the moment to be very clear about what kind of trouble that actually is, because it is easy to hear it as cosmic horror and miss the point the physicists are actually making. They are not concluding that you are a Boltzmann brain. They are concluding that any theory which predicts you probably should be one has failed a test. Consider a structural engineer again. If the blueprint for a bridge predicts that the bridge, standing empty on a calm day, will collapse under nothing but its own weight, the engineer does not gaze mournfully at the doomed bridge. The engineer treats the prediction as a warning light, a sign that something in the design is wrong, and goes back to the blueprints. That is exactly the posture Dyson, Kleban, and Susskind took. A cosmological model that predicts most of its observers are random fluctuations is a model with a serious internal fault. The horror is not evidence about you. The horror is a diagnostic. It is the theory telling on itself. There is a strange and admirable kind of scientific honesty in this, and it is worth naming plainly because it is the opposite of how people imagine science works. The field is using the sheer awfulness of a result as a tool. A cosmology that predicts a universe overrun with confused, isolated, memory-fabricating minds is, almost by definition, a cosmology that has gone wrong somewhere upstream, because it cannot even account for the reliable, ordered physics-doing observers who produced the theory in the first place. If your model predicts that the typical thinker is a momentary accident with fake memories, then your model cannot explain why you, a careful thinker checking real instruments and building consistent theories, exist at all. The prediction is self-undermining, and rather than hide from that, serious physicists have treated too horrifying to be true as an actual, technical reason to go back and check the math. Not because horror is evidence, on its own, of anything, but because a universe that mostly makes accidents is a universe whose physics probably contains a mistake. And that is the honest resolution of this chapter, the answer to the question of just how seriously the number is meant. It is meant completely seriously, and it is treated not as a prophecy of doom, but as a red flag on a piece of otherwise trusted mathematics. The 2002 paper did not announce that we are all brains in the void. It announced that the straightforward reading of our own best cosmology produces an absurd, self-contradicting prediction, and that therefore something in that reading needs repair. The disturbing implication is not really about you, it is about the equations. Somewhere in them, an assumption is quietly wrong, or an ingredient is missing, and the flood of accidental minds is how the error announces itself, which leaves one enormous question hanging, the one that turns this from a curiosity into a decades-long research program that is still unresolved today. Where does all that empty space and all that endless time actually come from? The whole calculation depends on a universe that expands forever and gives the trembling vacuum an eternity to work in. But why should the universe do that at all? Why is there so much space, so smooth and so flat, stretching out in every direction we look, and why should it keep stretching without end? To answer that, and to see how the Boltzmann brain problem gets not solved but dramatically worse, we have to leave the far future entirely and travel back to a single physicist, working alone late on a December night in 1979, who was chasing a small and technical puzzle, and who instead stumbled onto the mechanism that built the sky and scrawled 2 stunned words across the top of his notebook. On the night of the 6th of December, 1979, a young physicist named Alan Guth was working late, chasing a problem so narrow and technical that almost no one outside his corner of the field would have cared about it. He was 32 years old, without a permanent job, bouncing between temporary research positions, the kind of promising but unsettled young scientist who has begun to wonder whether the promise will ever cash out. The puzzle in front of him that night concerned a missing particle. Certain leading theories of the early universe predicted that the newborn cosmos should have produced enormous quantities of a strange object called a magnetic monopole. A magnetic monopole is a hypothetical particle with only one magnetic pole, a north with no south, which is deeply odd because every magnet anyone has ever made or found in nature has both. Snap a bar magnet in half, and you do not get a lone north and a lone south. You get two smaller magnets, each with both poles again. The theories said the early universe should have made monopoles by the truckload. Nobody, then or since, has ever detected a single one. Chasing that mismatch, Guth stumbled onto something incomparably larger than the puzzle he had set out to solve. By the time morning came, he had scrawled 2 words across the top of a page in his notebook, in block capital letters, boxed in, as if he needed to convince himself of the size of what he had just found. Spectacular realization. That notebook page survives. It sits today in a museum in Chicago, one of the few genuine artifacts marking the exact moment a picture of the entire cosmos changed. What Guth had realized, tracing the physics of that missing particle backward, was that the very early universe could have passed through a brief, violent, almost unimaginably rapid burst of expansion. Not the stately, gradual stretching of ordinary cosmic expansion, but an explosive doubling and redoubling of space itself, over and over, in the first tiny fraction of the first second. He would come to call it inflation. The mechanism behind it rested on a strange temporary condition that physicists call a false vacuum. To understand it, picture the energy of empty space as a landscape of hills and valleys where things naturally roll downhill toward the lowest point, the state of least energy, the true bottom. A false vacuum is a field caught not at the true bottom, but resting in a shallow dip partway up the hillside, a little ledge that feels for a moment like the lowest possible place, but is not. And a field trapped in that false higher ledge does something that no ordinary matter does. When you plug its condition into Einstein's equations of gravity, its pressure comes out negative. Ordinary matter has positive pressure, and its gravity pulls things together. This negative pressure does the opposite. It pushes space apart, violently. Space itself gets shoved outward, doubling in size, then doubling again, and again, faster than thought. The numbers are difficult to hold in the mind. In the tiniest sliver of the first second, a span far too short to be called an instant in any ordinary sense, inflation stretched space by a factor of at least 10 raised to the 26th power, a 1 with 26 zeros after it. A region far smaller than a single atom was blown up, almost instantaneously, into something larger than a grapefruit, and everything we can now see across billions of light years grew from a patch inside that. And here is the beauty of what Guth had found, the reason it deserved those 2 boxed words. Inflation did not just solve his original monopole problem by diluting the monopoles so thoroughly across the suddenly enormous space that essentially none would ever be found. It solved 2 other deep puzzles that he had not even been trying to solve, puzzles that had quietly troubled cosmologists for years. The first was the flatness of the universe. When you measure the overall geometry of space, it comes out astonishingly flat, balanced on a knife edge between curving one way or the other, and no one had a good reason for why it should be so finely balanced. Inflation explained it effortlessly. Take any curved surface and blow it up to a colossal size, and any patch of it you can see looks flat, the same way the ground beneath your feet looks flat, even though you stand on a round planet. The second puzzle was uniformity. Look in one direction with a telescope, then the exact opposite direction, at regions so far apart their light could never have crossed the gap between them, and they look nearly identical. The same temperature, the same texture. How could regions that never touched come out matching? Inflation answered that too. Those regions were once tiny and close, in contact, evened out together, and only then flung far apart by the sudden expansion. 3 stubborn puzzles, 1 mechanism. It was the kind of unification that makes physicists trust an idea. There is something almost too fitting about that word, false, sitting at the center of the whole thing, a false vacuum. A state of space pretending, for the briefest possible moment, to be the true and settled foundation of everything, before dropping through into what was actually underneath it all along. The universe we live in, on this picture, was born out of a lie space told itself, a temporary ledge mistaken for the bottom, and the correction of that error, the field finally rolling down to its true low point, released the staggering energy that became all the matter and light there is. Inflation was quickly recognized as one of the most important ideas in modern cosmology, and it has since passed real observational tests, correctly predicting subtle patterns in the faint afterglow of the early universe that later satellites went on to measure. But the false vacuum came with a side effect that nobody had planned for, a consequence that would end up mattering far more for this story than magnetic monopoles ever did. When physicists looked closely at how inflation was supposed to work, they kept running into the same uncomfortable feature. Once inflation starts, it is remarkably hard to make it stop. The very negative pressure that drives the explosive expansion also tends to keep the field trapped up on its ledge, still inflating, still doubling space, in region after region, faster than any single region can finish rolling down and settling into calm. Guth's original version had this problem badly. It could start inflation, but it struggled to end it gracefully, leaving a universe that kept blowing itself apart rather than settling into the quiet, star-filled cosmos we actually observe. That difficulty, the trouble of getting inflation to stop, looked at first like a flaw to be fixed. It turned out to be a door into something far stranger. Because when other physicists took up Guth's idea and worked out what happens when inflation refuses to fully end, they did not find a mistake to be patched. They found that a never-ending inflation was not the exception at all, but the natural default behavior of the whole process. And a universe where inflation never fully stops is not one universe. It is an endless, self-reproducing forest of them, sprouting off from one another forever, each one sealed away from all the others behind a wall of runaway expansion. That picture has a name, and it takes the Boltzmann brain problem, which was already bad enough, and makes it almost unmanageably worse. Imagine a storm at sea, an ocean under a hard wind, the surface heaving into waves of every size. In some patches the water barely stirs, in others it rears up into towering swells. There is no single height to the ocean, only a churning field of local peaks and troughs, each patch doing its own thing, unpredictably, from one stretch of water to the next. Now hold that image, because it is close to how the physicist André Linde asked us to picture the newborn universe, and it is the picture that turns inflation from a single event into something with no end. Linde was one of a handful of physicists who took Alan Guth's idea and asked the obvious follow-up question. Guth had shown how to start inflation. He had struggled to stop it. So what actually happens if it does not stop cleanly? The answers they found, arriving from different directions and different methods, kept landing in the same astonishing place. The trouble with Guth's original version was ending it, getting inflation to switch off everywhere at once, gracefully, to leave behind a calm universe full of stars, turned out to be far harder than starting it. Linde closed that gap, first in 1983 and then more radically in 1986, by dropping one of Guth's hidden assumptions. Guth had pictured the whole early universe flipping inflation on and then off together, in unison, like a single switch. Linde argued instead that different patches of space carry different starting values of the field that drives inflation, exactly like the storm ocean, where wave heights vary unpredictably from one patch of water to the next. Some patches never rise high enough to inflate at all. Others get shoved to enormous heights and take off, stretching by unthinkable factors before finally settling down into something that looks, from the inside, like an ordinary universe full of stars and rules and history. Then Linde pushed the idea one crucial step further, into what he called eternal chaotic inflation, and this is where the ground genuinely drops away. The field driving inflation does not sit still while space stretches. It keeps fluctuating, randomly, trembling up and down, and in some regions those random fluctuations happen to shove the field back up to a great height, kicking off brand new inflation all over again. In fresh patches, faster than the old patches can finish settling down. The process, once running, never runs out. It keeps generating new inflating regions endlessly, and inside some of them, inflation locally stops and cools into a calm, ordinary universe, while all around them space keeps right on inflating, spinning off more and more new pockets, forever. It is a fire that creates more fuel faster than it burns, and so it never goes out. The picture this leaves you with is called the multiverse, and it is important to be precise about what the word means here, because it is not the loose science fiction version. It means this. Inflating space, on Linda's account, is the permanent, eternal background condition of reality, and within it, calm, ordinary universes bubble into being without end, each one a pocket where inflation happened to stop. Our entire observable universe, everything we can see in every direction, all of it, would be just one of those cooled-off pockets, one bubble among an uncountable and still growing number of others. And every bubble is sealed off from all the rest by the very same runaway expansion that produced it. The space between the bubbles is inflating so fast that nothing, no light, no signal, no traveler, could ever cross from one to another. Each pocket universe is an island, permanently marooned, unable to see or reach or ever confirm the existence of any of its neighbors. There is a catch buried inside all of this that is worth pausing on, because it cuts against the word eternal in a surprising direction. You might assume that if inflation is eternal going forward, endlessly sprouting new bubbles, then it must also stretch back forever into the past, a cosmos with no beginning. In 2003, three physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, proved that this is not so. They showed that any universe that has, on average, been expanding throughout its history cannot stretch back infinitely into the past. It has to have a beginning. Eternal inflation, it turns out, is only eternal in one direction. Trace it backward far enough and you hit a genuine edge, a boundary that the theorem says must exist and that nobody has found a way around. The forest of bubbles grows forever forward, but it was planted at a definite moment. That is a remarkable result on its own, and we will not linger on it, except to note that even a multiverse had to start somewhere. Now watch what this does to the mind in the void. Everything we spent the earlier chapters establishing, the loophole, the trembling vacuum, the endless time in which the improbable becomes certain, all of it was already enough to conjure Boltzmann brains inside a single universe running down toward heat death. But eternal inflation does not give you one universe. It gives you an endless, ever-multiplying number of them, sprouting forever. The same bet that once applied to a single room full of air, and then to a single bubble universe, now applies across an infinite and still growing forest of bubbles. It applies to every mind that will ever exist inside any of them. And crucially, Lind himself has described what eternal, chaotic inflation predicts in the strongest possible terms. Not most possibilities realized somewhere. All of them. Every physically allowed variation of a universe generated endlessly forever, including, should the numbers work out that way, every possible variation of the exact thought you are having right now. That last phrase deserves its full weight. In a genuinely infinite, self-reproducing multiverse, anything the laws of physics permit does not merely have a chance of happening somewhere. It happens endlessly in an infinite number of places. There are, on this picture, an infinite number of ordinary observers, grown the slow way through billions of years of stars and biology. And there are an infinite number of accidental observers, Boltzmann brains, flickering out of the trembling vacuum of countless bubbles. Both populations are infinite, and that is not a comforting balance. It is the exact spot where the mathematics stops working the way mathematics is supposed to. Because the entire Boltzmann brain question was always a counting problem, a matter of comparing how many real minds there are to how many accidental ones. And you cannot compare two infinities the way you compare two ordinary numbers. Alan Guth, the same man who wrote Spectacular Realization in his notebook, saw this coming, and he has spent decades since confronting it. He likes to explain the trouble using cows. In a single ordinary universe, he points out, cows born with two heads are rarer than cows born with one head, and you can state exactly how much rarer just by counting them. But in an infinitely branching multiverse, there are an infinite number of one-headed cows and an infinite number of two-headed cows. So what happens to the ratio, which is rarer now? Ordinary arithmetic has no answer. Infinity divided by infinity is not a number. It is a warning sign, and that warning sign is about to become the single deepest problem in this entire story. Because when the two things you are trying to count are ordinary minds and accidental ones, the failure of the arithmetic is not an abstract inconvenience. It decides whether you should expect to be real. Here is a problem that sounds like a joke, and is, in fact, one of the deepest unsolved questions in modern cosmology. In an infinite multiverse, are two-headed cows rare? In a single universe, the answer is easy. You count the two-headed cows, you count the one-headed cows, and you compare. Two-headed cows are rare because there are far fewer of them. But in an eternally inflating multiverse, sprouting endless bubbles forever, there are an infinite number of one-headed cows and also an infinite number of two-headed cows. Both counts run to infinity. And infinity divided by infinity is not a number, it is a broken calculation. This is Alan Guth's own favorite way of illustrating what physicists call the measure problem. And behind the barnyard image lies the thing that decides whether you should expect your own mind to be real or accidental. The measure problem is, at its heart, the question of how you count things when there are infinitely many of them. In ordinary life, you never face it, because ordinary populations are finite. But the moment you take eternal inflation seriously, every category you might want to count, every kind of observer, every kind of event, becomes infinite. To get a ratio out of two infinities, you first have to choose a rule for how you are going to count them, a method for sampling the endless list in some order and taking the proportions as you go. Physicists call such a rule a measure, and here is the catastrophe at the center of it all. Different measures, each one perfectly reasonable looking on its own, give wildly, irreconcilably different answers. There is no single, obviously correct way to count, and the way you choose changes everything, including whether ordinary observers or Boltzmann brains come out on top. Consider one of the most natural counting rules you could pick, called the proper time cutoff. It has an intuitive logic. Count all the observers that exist up to a certain moment in time, then let that moment advance and take your proportions from that growing sample. Sensible enough. But run the numbers with this rule and out falls a result so strange it earned its own name, the youngness paradox. Because the multiverse is inflating and constantly making new bubbles, and because it makes exponentially more of them as time goes on, this counting rule concludes that observers in younger universes should vastly, overwhelmingly outnumber observers in older ones. For every fraction of a billion years you shave off the age, the number of observers explodes by a staggering factor. Follow that logic all the way down, and the single most common observer this rule predicts is not anything like you. It is a mind that has just this instant fluctuated into being, in a universe barely older than the fluctuation itself. Researchers call it a Boltzmann baby, a mind popping out of the hot chaos of a very young cosmos, holding memories of a life it never lived, lasting exactly as long as the accident that made it. Guth did not shrug this off, and neither did his colleagues. In 2010, he co-authored a paper with a group of physicists, its title reading almost like a confession, Boltzmann Brains and the Scale Factor Cutoff Measure of the Multiverse. Read that title again and let the strangeness of it settle. The man who discovered inflation, one of the triumphs of 20th century physics, spent part of his career trying to stop his own theory from concluding that people like him should not exist. That is the genuine, documented state of the field, not a fringe worry. A problem serious enough that the founders of the theory publish papers with Boltzmann brains in the title, hunting for a way to keep their own equations from predicting a cosmos overrun with accidental minds. Their proposed fix in that paper was a different counting rule called the scale factor cutoff, and it does manage to dodge the worst of the youngness paradox. But here is where the trap reveals its true shape, and why nobody in the field considers the matter closed. The fix turns out to sit on a knife edge. The counting rule has a central parameter, a dial you have to set, and the value you set it to determines the outcome. Nudge that dial one way, and the youngness paradox comes flooding right back, drowning you in Boltzmann babies. Nudge it the other way, and you fall into the opposite failure, which researchers have called an oldness paradox, where nearly every observer the theory predicts turns out to be a Boltzmann brain after all, just arriving from the far end of the same ledger instead of the near end. Tune the counting one way, and you drown in accidental minds from the young universe. Tune it the other way, and you drown in accidental minds from the old one. There is a razor-thin band in between where the answer comes out looking like us, and nothing in the theory tells you why the dial should sit exactly there. Not every serious attempt takes the same route, and it is worth knowing that the smartest people in the field have thrown genuinely different tools at this. The physicist Raphael Bousso built an entirely different kind of measure, called the causal diamond, out of black hole physics, rather than by patching the time cutoff directly. It sidesteps some of the worst tuning problems the other measures run into, and, impressively, it even makes a few real, checkable predictions about our own universe that turned out to match observation. That is not nothing. A measure that predicts correct features of the actual cosmos has earned a hearing, but it too comes with its own unresolved edge cases, its own awkward corners where the counting becomes ambiguous again. Different tool, same unfinished job. No version of the measure that physicists have tried gets to skip the fundamental choice, and every version pays for its choice somewhere. Step back and look at the whole landscape, and the honest picture is this. Dozens of proposed counting rules exist. Each one rescues some good results and breaks others. Tune the measure one way, and you are buried in Boltzmann babies from young universes. Tune it another way, and you are buried in Boltzmann brains from old ones. Find a clever rule like the causal diamond that avoids the worst of both, and you inherit a fresh set of edge cases nobody has resolved. There is not yet an agreed-upon rule that avoids every trap at once, keeps every good prediction, and rests on a principle everyone accepts rather than a dial tuned by hand to give the answer we wanted. And by Alan Guth's own admission, few physicists consider the underlying problem solved. That is not a gap in one explanation. It is the honest current state of an entire field, which is precisely why this was never a ghost story dressed up as physics. It is a live, unresolved argument sitting inside working equations, built and defended by the same people who built the theory in the first place, and they are still checking, right now, whether the universe they discovered has quietly made you one of its accidents. And yet, before you file this under unsolvable and walk away, there is a reason the field refuses to dismiss this kind of reasoning as clever but untestable. This exact move, this business of betting on whichever version of reality would allow an observer to survive and ask the question, has been tried before, once, pointed at a completely different target. It had nothing to do with minds. It was aimed at the invisible force stretching the whole universe thin, and it came back with a verified, checkable, dead right answer, years before anyone had the instruments to confirm it. The man who made that bet was Steven Weinberg, and his success is the reason nobody gets to wave this math away. In 1987, a physicist did something that, by every ordinary rule of science, should not have worked. Before anyone had built an instrument precise enough to test him, before there was any way to check, he sat down and wrote out a number. The number was a limit on the strength of the mysterious force that stretches the universe apart, the same force we would later come to call dark energy, the same force driving the long dark of the heat death. He reasoned that this force could be no larger than roughly 500 times the density of ordinary matter filling today's cosmos. It was a specific, bounded prediction, made from pure argument, with no measurement behind it. Then he waited. His name was Steven Weinberg, one of the towering figures of 20th century physics, a Nobel laureate who had helped unify the fundamental forces of nature, and his target was not a mind, not a Boltzmann brain, but the invisible pressure quietly deciding the fate of everything. The strange part, the part that makes this more than a lucky guess, is how he arrived at his number. Weinberg never measured that force. He could not. No one could, in 1987. Instead, he reasoned about it, using a version of the same cold arithmetic that this story has already turned on you, the arithmetic of which universes can contain an observer to notice them. His logic went like this. Suppose the strength of this stretching force could, in principle, have taken almost any value at all across the multiverse of bubbles. Most of the possible values spell disaster for the prospect of anyone existing. If the force were much stronger, space would have torn itself apart so violently, so early, that no galaxy, no star, no planet, no living thing could ever have formed. Matter would have been ripped into thin gas before gravity could pull it into anything. A universe like that is sterile. It never produces an observer, so no one is ever born inside it to wonder why its stretching force is so fierce. Only a narrow band of values, Weinberg realized, permits a universe gentle enough for structure to form, for galaxies to condense, for stars to ignite, for chemistry to become biology, for a mind to eventually arise and ask the question in the first place. And here is the move, the anthropic bet. If you find yourself existing, asking the question, then you must be in one of the rare, hospitable universes, because those are the only kind that produce questioners. So Weinberg bet that our stretching force must fall inside that narrow, life-permitting band near the top edge of what would still allow galaxies to form, and he calculated where that edge lay. Get the number wrong, and there is no drama, no story, no you sitting here to hear about it. Every version of the universe on the wrong side of that line failed silently, unwitnessed, with nobody left standing to notice it had even happened. A decade later, the universe answered him. In 1998, the same year and the same supernova measurements we met in the long dark, when Perlmutter, Schmidt, and Rius discovered that cosmic expansion was accelerating, astronomers finally measured the strength of the stretching force directly, for the first time, and the number landed exactly inside the band Weinberg had marked out 11 years earlier, before any telescope existed that could check it. He had reasoned his way to a real physical property of the cosmos, using nothing but the logic that a universe must be capable of producing a reader for his own paper, and reality confirmed it. He had bet on the only kind of universe that could contain someone to ask the question, and he had won. This is why the anthropic style of argument cannot simply be dismissed as unfalsifiable philosophy, a clever story that predicts nothing and risks nothing. Weinberg's success is a standing rebuke to that dismissal. This exact style of reasoning, weighing which universes can contain observers and betting accordingly, already produced one concrete number that reality confirmed, to within that factor of a few hundred, years before the measurement was possible. It has a track record. It made a real prediction, and the prediction came true. And that is precisely what makes the Boltzmann brain problem so difficult to shrug off. Because physicists run the very same kind of weighing when they compare two kinds of minds. One kind built slowly, over billions of years of evolution. One kind assembled in an instant out of the trembling vacuum. Count how many of each the multiverse should produce, and the numbers, under most counting rules, collapse hard toward the accidental kind by a margin too large to comfortably write out. Same engine, different question. Point that engine at the stretching force of space, and it lands on a number the universe confirmed a decade later, checked against a real sky full of real galaxies. Point the identical engine at the population of minds scattered across an eternally inflating multiverse, and it lands somewhere else entirely, on the uncomfortable conclusion that a randomly chosen mind should probably be an accident, You do not get to trust the engine when it hands you a triumph and disown it when it hands you a horror. That is Weinberg's own point, made repeatedly. The physicist Sean Carroll, whom we met at the very start, worried about exactly this excess of accidental minds, has spent years pointing to Weinberg's success as the reason the concern is legitimate. If the anthropic weighing is reliable enough to correctly predict the force stretching the cosmos, then, when the same weighing predicts a flood of Boltzmann brains, that prediction has to be taken seriously, not laughed off, which would be a tidy and genuinely horrifying place to leave things. The same trusted math that nailed the dark energy density also seems to say your mind is probably an accident, and you are not permitted to trust it in the first case and reject it in the second. Except that the entire bet, Weinberg's and everyone else's, rests on one buried assumption that almost nobody thought to question for decades. It rests on the idea that this stretching force, the cosmological constant, is exactly that, a constant, a fixed number, welded to the same value forever, the same in the deep past and the deep future, and now. Every calculation of the heat death, of the endless dark, of the tower of exponents wait for a stray mind to flicker into being, depends on that force never changing. And in 2024, on a mountaintop in Arizona, an instrument mapping tens of millions of galaxies found the first serious crack in that assumption. The ground the whole argument has been standing on may already be shifting, silently, underneath it. On a mountaintop in Arizona, bolted to the top of a telescope that has been staring at the sky since the 1970s, sits an instrument with 5,000 tiny robotic eyes. Each one is a slender optical fiber, and each fiber can swivel independently to point at a single distant galaxy, drink in its light, and pass it down to be dissected into a spectrum. The instrument is called DESI, and across the years since it began, it has mapped the positions and distances of tens of millions of galaxies, building the largest three-dimensional map of the universe ever made. Its purpose is to measure, with unprecedented care, how fast space has been stretching apart across the last 11 billion years of cosmic history. And in 2024 and 2025, when its results came in and were combined with older data, they pointed at something nobody had built into the earlier picture. The force stretching the universe apart may not be constant after all. It may be weakening. To feel why that single word, weakening, is an earthquake, remember what the previous chapters assumed at every step. The cosmological constant, the dark energy stretching space, was treated as exactly that, a constant, a fixed number, the same in the deep past, the same now, the same in the endless future. Every calculation of the heat death, every estimate of the tower of exponents wait for a Boltzmann brain to assemble. Every version of the long dark rested on that force holding its value forever. DESI's map, combined with older supernova measurements, suggested instead that dark energy was stronger in the past and has been fading as the cosmos ages, not vanishing, weakening. And a stretching force that changes over time is a completely different beast from one that holds steady, because it opens the door to an entirely different ending. The evidence, it must be said clearly, is not yet a proof, and the story of the number itself is a lesson in how careful physics has to be. The DESI result, combined with one particular catalogue of supernovae, reached a statistical confidence that physicists label 4.2 sigma. That sounds impressive, almost final, the kind of figure that ends arguments. It does not, and here is the humbling part. Swap the catalogue of supernovae underneath the analysis for a different one, and the number moves. Combine DESI with a catalogue called Pantheon Plus, and the same underlying signal drops to 2.8 sigma, distinctly weaker. Swap in a catalogue called Union 3 instead, and it climbs to 3.8. Only with the newest catalogue does it reach that headline 4.2. The conclusion literally shifts, depending on which set of exploding stars you trust to calibrate the distances. That is not a scandal. It is ordinary science, showing its work, and showing how far there still is to go. Physics has a deliberately punishing bar for calling something proven, and it is worth knowing exactly how high it sits. The threshold is 5 sigma. That is the same standard that had to be cleared before anyone was allowed to announce that the Higgs boson was real back in 2012. 5 sigma means the odds of the result being a fluke are smaller than roughly 1 in 3 million. Nothing about a weakening dark energy has cleared that bar. Not 4.2 sigma, not close. And in 2025, 2 cosmologists, Deng Wang and David Moter, went back through DESI's own numbers and found something messier sitting underneath the headline. The different data sets being stitched together, the faint afterglow of the early universe, the galaxy map, the supernovae, do not fully agree with one another even before you combine them. Stitch disagreeing data together, they argued, and the resulting number stops meaning quite what it appears to mean. Their own conclusion was not a clean dismissal either. Taken separately, the individual data sets do not confidently detect the change on their own, yet their combined analysis still lean toward a shifting universe. Nobody currently agrees on why. Nobody currently agrees on how much it should worry you. But what both sides agree on, oddly, is what is actually at stake, and it is enormous. If the number holds anywhere near where DESI put it, then the heat death may not be the ending waiting at the end of everything after all. Because if dark energy is not a fixed constant but a fading force, then some analyses built on the same result point toward the stretching, reversing entirely. Gravity, so long overpowered, finally winning. Expansion slowing, stopping, and folding back inward. The whole cosmos collapsing toward a fiery end that physicists call a big crunch. And the timescale for such an ending is not a tower of exponents. It is not a 1 followed by 100 zeros of years. Some estimates, built on this changing dark energy, put a possible collapse as soon as 20 billion years from now, a number almost small enough to feel close. Roughly the age the universe already is, again, and then done. Now watch what that does to the mind in the void, because for the first time in this entire story, there may be a genuine way out. The whole Boltzmann brain calculation, the one the earlier chapters spent so long building, only works if the universe keeps going forever. Every stray, randomly assembled mind needs an ocean of time to fluctuate into being. That tower of exponents, 50 zeros tall. A universe that keeps expanding into cold, empty vacuum for eternity has all the time such accidents require, and more. But a universe that ends in 20 billion years, folding back into itself, never gets anywhere close. Cut the clock short enough, and the odds of you being one of those accidental minds do not merely shrink. They round straight down to nothing. There simply is not enough time for the trembling vacuum to build even one. If the universe has an early, fiery end, the Boltzmann brains never get born. But whether that counts as good news is, of course, a separate and darker question. A reprieve from being an accidental mind, purchased with a fiery collapse of everything 20 billion years out, is a strange kind of comfort. And notice how narrow this escape actually is, because it only closes one door. Everything DESI measures, everything about a possible big crunch, concerns this bubble. Our one pocket of space, our single cooled-off region, in Linde's endless inflating forest. Even if our bubble ends early and clean, eternal inflation does not stop. Out beyond our horizon, past a boundary no telescope inside this bubble could ever see across, the wider structure may still be sprouting new bubbles forever, and the measure problem, the youngness paradox, the two-headed cows, none of it ever depended on the fate of our little pocket. It depended on the whole inflating forest. So one door closes, and the other stays exactly where it has always been, past the horizon, past any measurement, past anything an instrument built inside this bubble could ever reach. Which means that if we want a real answer, we have run out of places to look outward. There is exactly one place left to check. Not the universe, your own memory, the one piece of evidence you have been trusting this entire time without ever once verifying it. Set the multiverse aside for a moment. Forget the bubbles, the trembling vacuum, the tower of exponents. There is a second road to the same unsettling place, and it needs none of that machinery. It does not need inflation or dark energy or an infinity of universes. It needs only one very stubborn 17th century philosopher, alone in a heated room in the winter, trying to work out whether there was anything at all he could know for certain. His name was René Descartes, and in 1641, in a short book called Meditations on First Philosophy, he built a demolition machine and pointed it at his own mind to see what, if anything, would survive. He built it in stages, each one more radical than the last. First, he doubted his senses. Eyes and ears are fooled constantly by illusions, by distance, by darkness, and everyone already knows it from experience, so the senses alone can never be trusted as a foundation. Then he pushed harder. How do you know, right now, that you are not dreaming? A vivid dream feels completely real while it is happening, and there is no reliable test you can run from inside it to prove you are awake. That already loosens the floor considerably. But even that was not extreme enough for what Descartes wanted, which was to find something that could survive the worst attack imaginable. So he invented the worst attack imaginable. Assume, he wrote, not merely a world that occasionally fools you, but a world built specifically to deceive you. Suppose that some malicious demon of the utmost power and cunning has devoted all its energy to deceiving you. Under that demon's influence, the sky, the air, the earth, colors, shapes, sounds, every external thing become nothing but engineered illusions, dreams crafted to trap your judgment. Descartes was not being theatrical for effect. He was hunting, with real rigor, for a single fact the demon could not fake, no matter how total its power. And he found one. Even a demon powerful enough to fabricate your entire sensory world, every sight and sound and memory of touch, cannot fabricate the fact that something is, right now, doing the doubting. If you are being deceived, then you exist to be deceived. The very act of being fooled proves there is a you there to fool. This proposition, I am, I exist, he concluded, is necessarily true whenever it is put forward by me or conceived in my mind. That is the famous conclusion, usually flattened into 3 tidy words, I think, therefore I am. But the real version, buried in 400-year-old Latin, is far more precise and far more limited than the slogan it became. And the limitation is the entire point. Look carefully at exactly what that proof secures, and just as carefully at what it leaves wide open. What it covers is a single instant. Something is thinking, right now. Therefore, something exists, right now, to do the thinking. That is the whole guarantee. It certifies the present moment, and nothing else. Descartes never claimed the demon could not touch anything beyond that, and if you take his own thought experiment seriously, the demon very much can. The demon can still fabricate every memory you are currently holding of 5 minutes ago. It can fabricate the vivid sense that this very thought followed logically from an earlier one, when no earlier moment ever actually happened at all. The certainty Descartes found reaches only the present tense. Your childhood, your last conversation, the years that made you who you believe you are, none of it is covered by the same guarantee. It is a fortress with exactly one room secured, and every hallway leading out of that room left completely open. Now put that beside the Boltzmann brain, and the symmetry is almost eerie. Boltzmann's argument, from the very first chapter, never claimed a fluctuation had to build an entire universe to be convincing from the inside. It only had to build a mind, convinced it was standing in one. Descartes, working with nothing but pure logic 3 centuries before the physics existed, arrived at the exact same narrow flaw from the opposite direction. Both of them isolated the same single certain thing, the thinking happening now, and both of them left the entire past unsecured. But there is a crucial difference, and it is not in Descartes' favor. Descartes assumed there had to be an escape hatch. In the meditations that follow, he tries to seal the open hallways by arguing that a benevolent God would never permit such total, systematic deception, and that this divine guarantee is what finally lets him trust his memories and the world again. Whether that argument actually works is still debated by philosophers 4 centuries later. But notice what it reveals. Descartes needed to believe some guarantee was built into reality, keeping radical doubt from turning out to be literally true. Physics offers no such rescue. A Boltzmann brain does not require a demon of infinite power and cunning, patiently constructing false memories on purpose. It requires only patience and a universe old enough to let random chance produce, purely by accident, everything Descartes' demon would have had to engineer deliberately. There is no benevolent guarantee waiting at the end of the physicist's version. Different mechanism, same open hallway, except this time nobody built a door to close it. The thinking instant is real. What surrounds it, what came before it, nobody ever promised. And here is where the philosophy stops being a thought experiment and becomes a laboratory result. Because in the last few decades, psychologists have actually done it. They have built false memories, whole and detailed, inside real, healthy human minds, and the people carrying them could not tell them from the truth. It started almost by accident, as a class assignment. In 1990, an undergraduate named Jim Cohn, taking a course from the psychologist Elizabeth Loftus, tried planting a false memory inside his own family. He wrote up 4 short childhood stories about his younger brother, 3 of them true, and 1 entirely invented. The invented one described his brother, at around age 5, getting lost in a shopping mall, frightened and crying, then rescued by a kind elderly stranger and reunited with the family. His brother read all 4 stories. Over the following days, he began to recall the mall incident in his own words, adding details nobody had given him. The flannel shirt the old man supposedly wore, how scared he had felt. At the end, when told that one of the 4 stories was fabricated, he could not pick out which one. When finally told it was the mall, he did not believe it. Loftus and her colleague, Jacqueline Pickrell, formalized the method and published it in 1995, running it on 24 adult participants. About 1 in 4 of them adopted the fabricated lost in the mall memory as their own. And in a detail that is its own quiet horror, when finally told that one of their stories was false, 5 of the 24 pointed to a real memory instead, insisting the genuine one was the fake. The false memories were not even flawless copies. Participants tended to describe the mall incident with fewer words, and rated it as less clear and less vivid than their real memories. It did not need to be a perfect forgery. It only needed to be believed. In 2023, a separate team ran a careful, pre-registered replication of the original study, decades later, on a fresh set of participants, and found that roughly 35% adopted the false memory, an even higher rate than Loftus and Pickrell first reported. There is a limit to the effect, and the limit is almost as revealing as the effect itself. In a follow-up, the psychologists Kathy Pesdek and Shirley Hodge tried implanting a second kind of false memory alongside the mall story, the claim that the child had once received a painful, embarrassing medical procedure. Getting lost in a mall is the kind of thing that plausibly happens to any child, and it implanted at meaningful rates. The invasive medical memory barely implanted at all. Believability, it turns out, is not really about how vivid or emotional a false story is. It is about how easily it fits the shape of a life your mind already expects to have had. A convincing false memory does not need to be dramatic. It only needs to slot neatly into the story you already believe about yourself. Nobody in that laboratory needed a demon or a fluctuating patch of vacuum to pull this off. A few printed paragraphs and a few days were enough. Descartes and Loftus leave you in the same place from 2 different centuries, holding a working self whose present is certain and whose past cannot be fully verified from the inside by any test you could ever run. Which leaves exactly one honest question for the end of all this. And the strange thing is, it was never really a question for the physicists to answer. It was always yours. So here we are, at the end of a long walk through the dark. And the honest thing to do now is gather up everything we have seen and lay it out plainly, one piece at a time, before handing the last question over to you, where it has belonged all along. We began with a mind flickering into existence in the empty void, furnished with a whole false life, and a physicist named Sean Carroll telling us that the real worry was never you personally, but a crack in our best equations. We stood at a grave in Vienna, under an equation Ludwig Boltzmann never wrote, and watched a warm, troubled man defend the reality of atoms to his last breath, and die 2 years before the proof arrived. We poured milk into coffee and found in it the one direction the whole universe is willing to move, the second law, dug out of a steam engine by Sadi Carnot and named by Rudolf Clausius. We followed that direction to its end, the heat death, and watched 2 teams of astronomers in 1998 catch the universe speeding up toward it. We found the loophole Joseph Loschmidt accidentally pried open, that order returning from chaos is not forbidden, only staggeringly rare, and that rare, multiplied by eternity, becomes certain. We learned from Gibbons and Hawking that empty space never fully goes still, that it trembles forever with a faint warmth it cannot shed. We watched 3 physicists in 2002 calculate the tower of exponents, wait for a mind to assemble from that trembling, and treat the horror of the result as a warning light on their own equations. We met Alan Guth on a December night, scrawling spectacular realization across his notebook, and followed his discovery into André Linde's endless inflating forest of bubble universes, where counting observers breaks arithmetic itself, and 2-headed cows have no well-defined rarity at all. We watched Steven Weinberg bet on the strength of dark energy a decade before it could be measured, and win, which is exactly why nobody gets to wave this math away. And we climbed a mountaintop in Arizona, where 30 million galaxies hinted that dark energy might be fading, that our bubble might end in a fiery crunch soon enough to starve the Boltzmann brains of the time they need. Then we set the whole cosmos aside and found the same abyss waiting in a single 17th century room, in Descartes' demon, and in a shopping mall a boy was never lost in. Now the spine question returns, the one from the very beginning, and it is time to be completely honest about what physics can and cannot do with it. Every proof you own that your past really happened lives inside your head, right now, in this moment. If a mind can arrive already full of a life it never earned, what test could you run from the inside to tell a real life from a convincing one? And here is the answer physics actually gives, stripped of drama. It cannot tell you no, and it cannot tell you yes. What the field has genuinely established is narrower than either, and stranger than both. Nobody currently has a way of counting minds across a vast or eternal universe that cleanly avoids predicting far too many accidental ones, without simply tuning the rules by hand to dodge that exact conclusion. That is not proof that you are an accident. It is a gap. A live, unsolved technical gap sitting inside equations that are otherwise among the most successful ever written, held by the very people who wrote them. So the verdict is not the physicists to deliver, and they have been careful, consistently, not to pretend otherwise. Consider honestly where the weight actually falls. On one side, the measure problem is real and unsolved, and under many ways of counting, accidental minds win. On the other side, every instrument you have ever trusted, every experiment, every memory was assembled inside your own point of view, and none of it was ever built to detect the difference. And on a third side, quiet and easy to miss, is the plainest observation of all. The universe you actually find yourself in is orderly. It is lawful. Drop a stone twice, and it falls the same way both times. A Boltzmann brain, a mind fluctuated at random from noise, has no reason to find itself in a coherent, rule-abiding world that keeps making sense the longer it looks. The overwhelming majority of accidental minds would experience chaos, a reality dissolving into nonsense the instant they examined it. Yours does not. That is not a proof, but it is a real piece of evidence, and it sits on the scale, and it is yours to weigh. That is the honest shape of it. The physics has taken this as far as physics currently can, and where it runs out, it does not hand you a conclusion. It hands you the scale and the weights and steps back. The people who built modern cosmology are still working on the measure problem right now, still testing whether dark energy is truly fading, still checking whether the universe they discovered has quietly made accidents its most common kind of observer. Maybe they will close the gap and the accidental minds will vanish from the equations, and the strangeness will dissolve into a footnote. Maybe the crunch is real and our bubble ends too soon for any brain to ever fluctuate. Maybe the answer lies past a horizon no telescope will ever cross, and we will simply never know. All of those remain open, and anyone who tells you the matter is settled, in either direction, has stopped doing science and started selling a story. But leave the equations for a moment, because there is one thing in this entire account that never once depended on the measure problem, or on dark energy, or on the fate of a single bubble. It is the smallest and most certain thing there is, and Descartes found it 400 years ago, alone in a room, with nothing but his own doubt for a tool. Something is thinking, right now. Whatever else is true or false, whatever the demon faked or the vacuum assembled or the years did or did not actually contain, the thinking is happening. This instant is real. You are, right now, aware. That is the one room in the fortress that no demon and no fluctuation and no counting rule can ever take from you. The past may be unverifiable and the future uncertain, but the present moment, the raw fact of experience occurring, is the single thing you were never asked to take on faith. And maybe that is the quiet gift buried at the bottom of all this cold arithmetic. We spend our lives trusting the past to tell us who we are, and leaning on the future to tell us where we are going. And physics has just spent an hour showing that both of those are, in the strictest sense, beyond your power to fully confirm. What is left, what is certain, what cannot be counterfeited, is only this: the moment you are in, the awareness happening as these words arrive. Whether it rests on 80 real years or was assembled an instant ago in the dark, the experience itself is undeniably, unmistakably here. And that, it turns out, is the only thing anyone, real or accidental, ever truly holds. Not the past, not the future, only the flicker of now, which is somehow, against every improbability, aware of itself. So the next time you catch yourself certain of who you are, certain of where you have been, let the certainty rest a little more lightly than it did before. Not because your life is a lie. Almost certainly it is not. But because the one thing you can never fully prove is also the thing you least need to. You are here. Something is thinking these thoughts. Whatever built the mind having them, it is, in this exact instant, awake. And in a universe that spends eternity sliding toward the dark, obeying a law that never once makes an exception, the simple fact that anything at all is briefly aware of anything at all, real or not, earned or not, is stranger and rarer and more beautiful than any answer we could have reached. Let that be enough to carry you into sleep. The equations will still be unsolved in the morning. The scale will still be in your hands. And the moment you are in right now, this one, the only one you were ever promised, is quietly, undeniably yours. Good night.